What if Einstein's theory of gravity, the very foundation of modern physics, wasn't the final word? For more than a century, general relativity has stood as the ultimate description of how the universe works. It has predicted black holes, explained the bending of light, and guided spacecraft through the solar system with astonishing accuracy. But what if there's more to the story? What if the equations that changed our understanding of space and time are only part of the truth? This is where Claudia de Rham comes in, a physicist who dares to ask the questions even Einstein couldn't answer. And her work might change everything we think we know about the cosmos. Claudia de Rham isn't just a scientist. She's a gravitational explorer, venturing into the frontiers of theoretical physics where the known laws of nature begin to fray. Her mission is bold: to find a deeper theory of gravity, one that not only matches Einstein's brilliance in explaining the known universe, but also solves the mysteries his equations can't. Chief among those mysteries is one of the strangest discoveries in modern science: the accelerating expansion of the universe. According to general relativity, gravity should pull matter together. Yet, the cosmos is speeding apart, as if pushed by an invisible force we call dark energy. Einstein's theory has no natural explanation for this. And that's where de Rham's revolutionary ideas come in. She works on a concept known as massive gravity. In Einstein's theory, the particle that carries the gravitational force, the hypothetical graviton, has no mass. It's massless, which allows gravity to have an infinite range, stretching across the universe. But de Rham's work dares to imagine, what if the graviton actually had a small mass? Not enough to break the universe, but just enough to subtly alter the behavior of gravity on cosmic scales. If true, this could naturally explain why the expansion of the universe is accelerating without the need for a mysterious dark energy field. Massive gravity isn't just a wild guess. De Rham has spent years developing it into a mathematically consistent theory, something that had eluded physicists for decades. Earlier attempts at massive gravity always ran into fatal problems, predictions that contradicted observations, or mathematical inconsistencies that rendered the theory unstable. But in 2010, de Rham, along with collaborators Gregory Gabadadze and Andrew Tolley, constructed a version of massive gravity that avoids these pitfalls. The result is now known as the DRGT theory, named after its creators, and it has opened an entirely new branch of gravitational physics. If massive gravity is correct, the implications are staggering. It means the universe's accelerating expansion isn't being driven by some exotic invisible energy. It's simply a consequence of how gravity works on the largest scales. It would mean that Einstein's general relativity, while brilliant, is an approximation of a deeper truth. And it would mark one of the most profound shifts in our understanding of nature since Einstein himself. But theories live or die by their predictions, and de Rham knows this. Her work doesn't stop at the blackboard. She's designing ways to test massive gravity using observations of cosmic structures, gravitational waves, and the motion of galaxies. Even the way light bends as it travels across billions of light years could reveal whether gravity truly behaves as Einstein thought, or whether Claudia de Rham's vision is the one nature follows. The stakes couldn't be higher. If her ideas are proven right, it would rewrite textbooks, reshape cosmology, and force physicists to rethink the fabric of space-time itself. And even if massive gravity turns out to be wrong, the process of testing it will push our understanding of the universe to unprecedented depths. Claudia de Rham is part of a rare breed of scientists willing to challenge the most sacred pillars of physics, not out of defiance, but out of necessity. because science advances by asking uncomfortable questions. And few questions are more uncomfortable or more thrilling than asking, was Einstein wrong about gravity? Challenging Einstein is not something done lightly. His theory of general relativity has been confirmed by every experiment thrown at it for over a century, from the bending of starlight during a solar eclipse to the detection of gravitational waves rippling through the cosmos. But Claudia de Rham understands that no theory is sacred if it can't explain everything. And there are cracks in Einstein's masterpiece, subtle but undeniable. One of the biggest cracks is the accelerating expansion of the universe, first discovered in 1998 by observing distant supernovae. According to Einstein's equations, the expansion should be slowing down, not speeding up. To make the math work, cosmologists invented the concept of dark energy, an invisible, unknown form of energy that makes up about 70% of the universe and pushes space apart. But this explanation is unsatisfying. We have no direct evidence for dark energy's existence, and it feels suspiciously like a patch to cover up a deeper problem. De Rham's massive gravity theory offers an elegant alternative. Maybe space expands faster because gravity itself weakens over vast distances, and this is a natural consequence of a graviton with mass. Her vision is as audacious as it is precise. In massive gravity, the graviton's tiny mass would act like a long-distance modification of Einstein's laws. Close to Earth, gravity would behave exactly as general relativity predicts, so satellites, planetary motion, and solar system experiments would match reality. But on intergalactic scales, the equations would shift just enough to explain the cosmic acceleration without inventing an entirely new form of energy. This subtle deviation could be hiding in plain sight, detectable only when we study the largest structures in the universe. Testing this idea requires combining cutting-edge astrophysics with some of the most advanced observational tools ever built. Claudia de Rham and her collaborators are looking to missions like the European Space Agency's Euclid Telescope, NASA's Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory. These instruments will map the distribution of galaxies and measure the bending of light from distant quasars with unprecedented accuracy. If massive gravity is real, its fingerprints should be etched into these cosmic patterns. But that's not the only battlefield for testing gravity. The discovery of gravitational waves in 2015 opened a new era of astronomy, one where we can listen to the universe. General relativity predicts exactly how these ripples should propagate through space-time. But if gravitons have mass, gravitational waves would travel slightly differently, slower than light, and with distortions in their waveform. The detectors at LIGO, Virgo, and Cagra are now sensitive enough to look for these minute deviations. A single confirmed anomaly could be the first sign that gravity is not what Einstein imagined. Of course, the scientific community is cautious. Modifying gravity is a high-risk, high-reward endeavor. History is littered with failed attempts. But de Rham's persistence and mathematical rigor have earned her deep respect in the field. Her theory is not a speculative guess. It's a carefully constructed framework that avoids the fatal flaws of its predecessors. In physics, that's rare. And it's why massive gravity is taken seriously. There's also a philosophical weight to her work. If massive gravity is correct, it challenges our perception of the cosmos on the most fundamental level. It suggests that the force binding planets, stars, and galaxies isn't infinite in reach, but finite. It means the universe has an intrinsic scale beyond which gravity simply fades away. And it forces us to ask, if gravity has limits, what else does? Could the universe itself be bounded, its expansion not just a feature of space, but a consequence of the rules that govern it? For Claudia de Rham, these questions are not abstract. They are the driving force of her career. She sees herself as part of a long lineage of physicists, each building on the work of those before them. Newton replaced Aristotle. Einstein replaced Newton. And now perhaps it's time for someone to take the next step. Whether massive gravity is the future or just another rung on the ladder, her journey embodies the essence of science: to never stop asking and never stop testing, even when the answers threaten the foundations of what we believe. To understand just how radical Claudia de Rham's proposal is, we need to step inside the mathematics of gravity itself. In Einstein's theory, gravity is not a force in the traditional sense. It's the curvature of space-time caused by mass and energy. Objects follow the curves and folds of this four-dimensional fabric, and light itself bends along the way. This picture has survived black holes, neutron stars, and the first images of event horizons. But it rests on a key assumption, that the particle carrying gravity, the graviton, has zero mass. Massless particles, like photons, can travel forever without slowing down. If gravitons are massless, gravity's influence extends infinitely. But if they have even the tiniest mass, the story changes dramatically. A massive graviton would give gravity a range limit, much like how radio waves weaken over distance. This would mean that on the scale of galaxies and beyond, gravity wouldn't pull as strongly as Einstein predicted. Space itself could then accelerate outward, not because of dark energy, but because gravity simply runs out of reach. This idea isn't new. Physicists first toyed with massive gravity in the 1930s, but the equations always fell apart. Adding mass to the graviton caused strange mathematical inconsistencies, like predicting ghost particles with negative energy, which violate the laws of physics. For decades, it seemed impossible to make massive gravity work without breaking the universe. That is, until Claudia de Rham came along. In 2010, she and her collaborators developed a breakthrough, a ghost-free theory of massive gravity. By carefully constructing the equations, they avoided the fatal inconsistencies that had doomed earlier attempts. This model, now known as the de Rham-Gabardadze-Tolley (DRGT) theory, gave physicists, for the first time, a mathematically consistent way to give the graviton mass. It was a turning point, transforming massive gravity from a fringe curiosity into a serious contender in cosmology. The beauty of DRGT theory is that it seamlessly matches Einstein's predictions in all the places we've tested them, like the solar system, while still allowing for differences on the largest scales. It's a surgical adjustment to the laws of physics, invisible up close but potentially revolutionary across billions of light years. And here's where it gets fascinating. If DRGT theory is right, we might already be seeing its effects without realizing it. The apparent need for dark energy could be nothing more than a sign that gravity is weaker at cosmic distances. The unexplained Hubble tension, a growing conflict between measurements of the universe's expansion rate, might be hinting at the same truth. What we've been treating as separate mysteries could, in fact, be two symptoms of one underlying cause. Proving this won't be easy. The differences between massless and massive gravity are subtle, requiring measurements of exquisite precision. But the technology to test them is arriving now. Upcoming surveys will track the distribution of galaxies, gravitational lensing patterns, and cosmic microwave background distortions with more detail than ever before. Each data point will be a clue, each anomaly a possible whisper from the fabric of space-time itself. De Rham knows the odds. Most new theories fail under scrutiny. But she also knows that without taking risks, physics cannot progress. Einstein once said that imagination is more important than knowledge, because knowledge is limited, but imagination embraces the entire world. In Claudia de Rham, we see that same spirit, a willingness to imagine a universe different from the one we think we know, and the determination to prove whether that vision is real. If she's right, it won't just solve the mystery of cosmic acceleration. It will reshape our understanding of the universe's architecture, rewriting one of the most successful theories in the history of science. And if she's wrong, the search will continue, guided by the questions she dared to ask. Testing Claudia de Rham's ideas requires looking at the universe on its grandest scales. One of the most promising tools for this is gravitational wave astronomy. When two massive objects like black holes or neutron stars collide, they send ripples through space-time itself, ripples that travel at the speed of light, according to Einstein. But if gravitons have mass, those ripples would behave differently. The waves might lose energy over long distances, arrive slightly later than expected, or have their frequencies subtly distorted. By studying these differences, physicists can place tight limits on the graviton's possible mass, or perhaps even detect it. The first detection of gravitational waves in 2015 was a triumph for Einstein's theory, matching his predictions almost perfectly. But the measurements are still young. As detectors like LIGO, Virgo, and the upcoming space-based LISA observatory become more sensitive, we'll be able to test for deviations so small they were previously invisible. For de Rham, this is an exciting moment, the first time in history when we can directly probe gravity's behavior across cosmic distances, potentially catching it in the act of fading. Massive gravity also has deep implications for the fate of the universe. In the standard picture, if dark energy is truly a constant, the cosmos will expand forever at an accelerating rate, becoming colder and emptier until all that remains is a thin, dark mist of particles, a scenario called the heat death of the universe. But if the acceleration is caused by gravity's range limit instead, the story could be very different. The expansion might slow down in the far future, or even reverse. Entirely new cosmic destinies open up, from endless oscillations to sudden collapses, depending on the graviton's exact properties. And then there's the philosophical shift. Einstein's theory taught us that gravity is geometry, the shape of space-time. De Rham's work suggests that gravity might be more like a field with its own particles, rules, and limits. This doesn't just change equations, it changes our mental image of reality itself. If gravity can fade, then the connections that hold the universe together are not eternal. Even the structure of space and time may have an expiration date. Claudia de Rham's journey from a young student fascinated by the cosmos to a physicist reshaping our understanding of it is a testament to curiosity and persistence. Her work stands at the intersection of theoretical elegance and experimental possibility, a rare and powerful place in physics. She's part of a new generation of scientists who are not content to simply extend Einstein's legacy, but who are willing to challenge it when the universe's riddles demand more. It's possible that in a few decades, we'll look back and see massive gravity as one of the great scientific revolutions of the 21st century. Or we might see it as a brilliant stepping stone that guided us toward the true explanation of cosmic acceleration. Either way, the questions Claudia de Rham is asking today will shape the future of physics. Because to rewrite Einstein is not to erase him, it's to continue the dialogue he began with the universe, a dialogue that may never truly end. Of course, rewriting Einstein's theory isn't something done lightly. General relativity has withstood more than a century of rigorous testing. From predicting the bending of starlight during eclipses to explaining the precise orbit of Mercury, to enabling GPS satellites to work correctly, it has proven itself again and again. To challenge it means stepping into a scientific arena where the bar for evidence is extraordinarily high. De Rham knows this and embraces it. In her view, the point isn't to discard general relativity, but to expand it, to discover where it might bend or break when confronted with the deepest mysteries of the cosmos. One of the strongest motivations for her work is the cosmic acceleration discovered in 1998, when astronomers found that distant supernovae were fainter than expected, evidence that the universe's expansion was speeding up. The simplest explanation was dark energy, a mysterious form of energy pervading space itself. But more than 2 decades later, dark energy remains a placeholder name for something we do not understand. For de Rham, this uncertainty is an opportunity. Perhaps the phenomenon isn't an unknown energy at all, but a sign that our description of gravity is incomplete. Testing such an idea requires creativity as well as precision. De Rham and her collaborators explore not only gravitational waves, but also the subtle ways that massive gravity could affect the growth of cosmic structures. Galaxies don't just float in space, they clump together under the pull of gravity, forming vast webs and clusters. If gravity's reach is finite, that clustering should be weaker at the largest scales, leaving detectable fingerprints in the cosmic web. Surveys like the Dark Energy Spectroscopic Instrument, DSI, and the upcoming Vera C. Rubin Observatory are mapping billions of galaxies to look for exactly these patterns. But perhaps most fascinating is how de Rham's work connects the very large with the very small. The graviton, if it exists, would be a quantum particle. This means that testing massive gravity isn't just about cosmology, it's also a step toward the long-sought unification of quantum mechanics and general relativity. Finding evidence for a massive graviton would force physicists to rethink the quantum structure of space-time, potentially offering clues toward a full theory of quantum gravity. Claudia de Rham's willingness to navigate this frontier, between theory and observation, between the classical and the quantum, makes her one of the most compelling voices in modern physics. She's not just following the data, she's crafting bold new frameworks for interpreting it, frameworks that could reshape our place in the universe. In the end, whether massive gravity turns out to be the correct path or not, her work embodies the essence of science, the courage to question even our most cherished truths, and the imagination to envision alternatives.